So, lecture 1 of computational methods, and in this lecture we are going to talk about two numerical methods. One is numerical integration and the other is numerical differentiation. And if you want to look this up in the book, so I'm referring to Newman's book over here. This is chapter 5. I'll also take bits and pieces from some of the other references, so you can always go and take a look at them, or of course any other material that you might find online. Okay, so first, just to give you a mathematical background, what does integration actually mean? Suppose I have some function f as a function of x. Let's say this is the function f of x, and I want to integrate this from some a to b. Then what I'm actually trying to do is I'm trying to find the area under the curve. So this area is what I'm interested in calculating. That is the mathematical interpretation of the process of integration. So integral f of x from a to b over x. So just integral f of x, suppose it is some function capital F, and that from a to b. So this is f at b minus f at a. So this is the meaning of integration. Okay, so how does one actually calculate it? In real analysis, there is something called Riemann integration. I'm not sure if you've done it yet in your maths course. Basically what that says is that you divide this function, you divide this space a to b into a large number of small slices, and then you treat each of these as a rectangle. So each of these little things is a small rectangle, and you know how to calculate area of a rectangle, right? So then you add up the areas of all of these rectangles, and the sum total of those is a close approximation of the actual integral of this function. And of course, if you want a more accurate answer, then you want to make your triangles as thin as possible, because the error is coming because you are approximating this sloped line to a straight kind of rectangle. So the more slices you have, the smaller each slice becomes, and then your answer becomes more and more accurate. So what we are saying is you divide this b minus a, this distance, into n slices. So number of slices or steps is n. Then the width of each bin, which I'm calling h, is b minus a over n. So this is the size of each slice. And what I can do is I can define x. So each of these points over here along the x-axis, I can denote it as xi, which is a plus I h. So you can see that when I is equal to 0, then xi is just a, so x0 is a. And if I is equal to n, then xi or xn is just b. So these are n steps, and their locations are given by x0 to xn, starting from x0, which is a, going all the way up to x0, which is b. And the xi is giving you the location of each of these points over here. So now how would you find the area? So let me zoom in into one part of the function. Suppose zooming into this part. So this is xi and this is xi plus 1. So this is just one slice. Then what I might want to do is the area of this slice is given by this width, which is h, times this value of the function. But where should I evaluate this function? Should I evaluate it at xi, in which case I will get this value? Or should I evaluate it at xi plus 1, in which I will get this value? So I guess one compromise could be, let's take the midpoint of these two. So I will evaluate this function f not at xi or xi plus 1, but at xi plus 1 over 2. And if you plug in this formula for xi over there, then you will see that this is just f of a plus I. So one is IH and the other is, oh, it will be I plus half H. Oops. So this xi is a plus IH. This xi plus 1 is a plus I plus 1 H. So in between them, it must be a plus I plus half H. So area of this one slice, or this is the ith slice, is just h times f at this. And so the total area under the curve from A to B, this will just be, so if I call this AI, so this will just be the sum over all the AIs. So you can find out then what the total area will be. So this is the basic principle of what is called Riemann integration in mathematics. Actually, Riemann integration is a little more formal than what I have defined. There you take the least possible area that you can get, which is at this point xi. Then you take the maximum possible area that you can get, which is at this point xi plus 1. And then you have to show that as the bin width decreases, then these two converge to each other, and the limit of convergence gives you the actual Riemann integral. Anyway, you will see it in your maths course whenever you do. So this is the basic philosophy of any integration routine. Any kind of numerical integration you want to do, essentially you want to add up a large number of small slices. Okay, but we can do better. We can improve. So what I've shown over here is just like some sort of quick and dirty algorithm to quickly do it. We can do a little better than that. So let's talk about what is called the trapezoid rule. For calculating the integral. So once again, let me just talk about one specific bin. So suppose this is my function, and suppose this is my xi plus 1. So earlier I said, why don't we just take a rectangle like this, either this way or this way or this way. Now we are going to try and improve this. We are going to say, instead of taking a rectangle, why don't we take a trapezoid or a trapezium? I don't know which term you're familiar with. So here is a trapezium, this entire thing. And if you remember from your school geometry, area of a trapezium or trapezoid is half times height times sum of the two parallel sides. So over here in our case, the height is just this h. This parallel side has size f of xi, and this has size f of xi plus 1. So area of each slice is half times height times f of xi plus f of xi plus 1. If you don't mind, I will just use a shorthand notation over here and say, so f of xi I will write it as fi, and f of xi plus 1 I will write it as fi plus 1. But you know what that means. That index just stands for which point we are evaluating it at. Okay, so this is area of one slice. So total area over the entire range of integration is going to be the sum over all the slices. So this is going to be so if we start evaluating this, this will become, so I goes from 0 up to n minus 1. So this becomes f0 plus f1. This is for the first slice. For the second slice, you get f1 plus f2. For the third slice, f2 plus f3. Da da da. In the end, you will get fn minus 2 and n minus 1. And finally, n minus 1 and fn. Or, now you will notice f1 comes twice, f2 comes twice, f3 will come twice. They will all come twice except for the first one and the last one. Those only come once. So this is h by 2 f0 plus twice f1 twice f2 twice fn minus 1, but only one times fn. Or I can write this as h over 2. So f at 0 is just f of a, and f at n is just f of b, because 0th point is a and point is b. So this is f of a plus f of b plus 2 times summation over all of the other. So 1 to n minus 1. So this is the formula for trapezoid rule. So given any function that you have, if I ask you to integrate this function from a to b, first thing you need to do is you need to check, first you need to decide how many points how many slices you want to divide this into. And of course, more slices you take, the more accurate your answer will be. So once you know how many points n you want, then you know what is h, because h is just b minus a over n. Then you list out all of the points xi from 0 to n. So you know which of these points you're interested in. Then you evaluate the function at each of those points, and then you apply this formula. This will give you a good approximation for the value of the integral. Okay, so what we're going to do is we're going to try and write a program to do an integration using trapezoid rule. So let's just take some simple function. Let's take integral over sine x from 0 to pi. And we know that this, the answer to this has to be 2. So let's quickly write down a function. So what do we need? We need to define the limits of our integration. So let's say a equals 0, b equals pi. Well, I guess then first I need to define pi. So I'll just bring it from numpy import pi, and we are going to be using sine also. So I'll import sine. Okay, good. So A and B have been done. Let's decide how many steps should we take. Let's take, let's just take 5 steps. Let's see what happens if we just integrate using 5 steps between 0 and pi. We expect we won't get an answer that's very accurate. Let's see. So then once we do this, we know that h is b minus a divided by n. Okay. And now I think we are set. Yeah. So let's start a loop for I in range 0 to n. Well, I should take n plus 1 because I want. So remember, in Python, when you put this range function, then it goes. So if I say 0 to n plus 1, it starts from 0 and then it goes until but not including n plus 1. So this will go 0 to n. Okay. So for this I, what should I do? Let's define the xi. So xi is defined as a plus I times h. Okay. Let me first initialize over here something called sum. So sum equal to 0. And now over here, I'm going to say sum is equal to sum plus sine of xi. Right. So basically, each time I'm calculating sine of xi and adding it to that sum. But notice first, if I is either 0 or n, I need to add it only once. But for all the other cases, I need to add it twice. That is what trapezoid rule says. So, how should I do this? Okay. So why don't I start from here itself? So first I'll just add the first and the last bits. So let's just say sine of A plus sine of B. So this part is taken care of. Now I don't need to do from 0 to n plus 1. I can just go from 1 to n because the 0th and the nth points have been taken care of. So here I have defined my xi, and then over here in the sum I'm going to add 2 times this. Great. So now my sum is taken care of, is it? FA, FB, and twice the sum of all the other ones. Perfect. So now I can come out from my for loop, and now I have to multiply by h by 2. So sum is equal to sum times h by 2. Okay, I think we're done. So let's print the answer, print sum, and this should work. Let's see. So remember, the answer we're looking for is 2. So let's run it. Okay, so we got an answer 1.9337 something. Here is the answer. So we expected it wasn't going to be very accurate because we only took 5 steps. So let's increase it. Let's take 10 steps and see what happens. We expect the answer to become more correct, more with a smaller error, more precise. Okay, so it was earlier 1.93 it was, now it's become 1.98. Okay, let's increase even more. So 100. Okay, now you see 1.998. Let's go to 1000 steps. You can see it's going quite. Now we have 1.999998. So it's getting really close. So obviously, the more steps you take, the more accurate your answer will become. But I don't know if you've noticed, but the program is also taking slightly longer to run each time. Okay, still not. If I increase this by a factor of 100, okay, please don't hang. Taking its sweet time. So you see, it's a trade-off, no? If you want a more accurate answer, your program will take a longer time in getting there. So you decide based on your whatever research requirement that you're doing for which you need this numerical integration. You need to decide for yourself whether like how much accuracy you want and how much time you're willing to spend on it. So that's a trade-off that one needs to deal with. Oi, why are you not going? There you go. So it took a good amount of time, but we've got 1.99999999999. Okay, at least up to 12 digits, it's given me 1.999. Okay, good. So we've seen the effect of taking large number of steps in terms of becoming more accurate, but also in terms of taking much longer to run. Okay. What if instead of sine, I wanted to integrate sine square over the same range? So wait, first let's cut this down. Let's just take 1000 steps, let's say. Instead of sine, I want to do sine square. So sine square, sine square, sine square. What should the answer be? Integral sine square from 0 to pi. I think pi by 2. So 1.57. Let's check. Yeah, okay, so 1.57 something. Okay, now you noticed that over here, when I changed from sine to sine square, there were 3 places I had to change it in. I had to change over here, over here. So this was for the first and the last term, and I had to change it inside over here for the intermediate term also. Now this is actually a little inefficient because, you know, suppose it wasn't just going from sine to sine square. Suppose I had to put in some complicated function like e to the power x plus cosine of x cube or some such thing. It's annoying to have to change it over and over again. Not just annoying, it also increases the chances that you might make a mistake somewhere in changing it. So instead of writing it multiple times, it's always a good programming practice to just define the function beforehand. No? So let's say define, I'll call it func of x, and I will say return sine square x. That's it. So now everywhere, instead of writing this sine square a everywhere, I will just write func of a func of b and this is func of xi. There's some error there. Wait, let me try and run this again. Yeah. So you're getting this. And now it's easy to change it. So suppose now instead of integrating sine square x from 0 to pi, let's say I wanted to integrate cosine x from 0 to pi. How much is cosine x from 0 to pi? Should be 0. I have not imported cosine from numpy. Fair enough. My bad. Let's try again. There you go. So you get some 10 to the power minus 16. So that is essentially 0. It's just machine precision. So there you go. So any function now that you want to change, if you want to change the function you're integrating, instead of having to type it out multiple times, you just put it once over here, and that's the end of the story. So that's an example of how you might use numerical integration. Here specifically we took the example of the trapezoid method.